Here at the University of Montana, continuing our discussion of Diophantine equations, section 2-5 in the Burton text on Math 326 number theory. So I guess we'll scroll down here to get to where we were. We took a look at this Diophantine equation. We came to a conjecture, and the conjecture, I guess, loosely stated, was this one, that if we have a Diophantine equation of form ax plus by equals c, then it has a solution if and only if D divides C, where D is the GCD of A and B. And if we have any particular solution, X naught, Y naught, then all the other solutions can be given by X naught plus B over D times T and Y naught minus A over D times T, where T is any arbitrary integer. Okay, so this seems to be the general solution to a Diophantine equation, and I guess we should probably prove this large statement. So I'll go to my overhead and we'll talk about a proof for this statement. Okay. Okay, so what's our hypothesis? Our hypothesis is this. If we are given a Diophantine equation, and I'll assume you know the definition of that, ax plus by equals c. It has a solution if D divides C, where D is equal to the GCD of A and B, and if X naught, Y naught is a particular solution, then all others, let's call it all other solutions, are given by what? Well, let's see, X is equal to X naught plus B over D times T, and Y is equal to Y naught minus A over dt. Okay, so that's what we're trying to prove. Let's go to a proof. So I'm only going to prove the, oh, and I should be careful here. I should say about t, you know, what is this t thing, where t is an integer, okay? So proof, I'm going to do the proof of the second assertion. So the second assertion is the case that these are the solutions. The fact that it has a solution if and only if D divides C, and that is an if and only if. I guess I could put a double F there. That we already proved in previously. So really, what we want to know are these really the two general forms of solutions for Diophantine equations if a solution exists? So off we go to the races. So let's see. Let's assume that X naught and Y naught is a particular solution. Let's go to now. Let's see if we can find another solution. So in other words, once we know X naught, Y naught, how do we find another solution? And what we'll hope to find is that other solution will be of these two forms. So let's let X sub 1 and Y sub 1 be another solution. So what does that mean? Well, so I guess what I mean is that if it's another solution, what we would have is AX1 plus by1 is equal to c. So let's see, let's start over here. ax1 plus by1 is equal to c. So ax naught plus by naught is also equal to c. So what does that mean? We can use those two pieces together to conclude that x1 plus by1 must be equal to ax naught plus by naught. That will certainly work. So combining like terms and factoring out, we could say, or equivalently, we could write this as a times x1 minus x naught is equal to b times y naught minus y1. And we'll call that equation 1 because we're going to be referencing back to it. So now, if we know that D is equal to the GCD of A and B, we have what? Well, we can say that A must be some multiple of D, so let's call A D times R, and B must be some multiple of D, so let's call that D times S. For some R and S in the integers. Okay. So I can see that we have some substituting we could do. We could put these values of A and B in for those values of A and B up there. So let's go ahead and do that next. So by substitution, we can construct what? Let's see what this thing looks like when we sub that in. So A becomes dr, so we have dr times x1 minus x naught, and that's the same thing as ds times y naught minus y1. Well, if we've got two d's in there, we could just divide that out. So we could say that implies that r is x1 minus x naught. R times x1 minus x naught is s times y naught minus y1. Okay. And let's call that equation 2. Now, let's see. So let's just think a little bit about this. We're going to use if we use the GCD of A and B is equal to D, what does that imply? Well, if we kind of think about what A and B are, so A is D times R and B is D times S, right? So let's see, that means that the GCD of D times R and D times S must be equal to D, which implies, well, there's a common D to all of these, so we have a theorem that says anytime there's a factor that's common to all, and we can factor it out. So or we can cancel it in this case, right? So the GCD can be rewritten as this, the GCD of R and S, and that must be equal to 1, right, if we take the greatest common divisor out of all of these. So there's a theorem that allows us to do that. So let's just think about this. What that means is that R and S up here are relatively prime. So since this thing is a multiple of R and it's relatively prime to S, that must mean that R is contained in y naught minus y1. And vice versa, since S is relatively prime to R, but S certainly divides this product over here because it's a factor on the right-hand side. So that means S must divide x1 minus x naught. So let's, and that's Euclid's lemma, right? So if we apply Euclid's lemma, then what can we say? Let's apply it to equation 2. And we can say that R must divide, it has to divide this side, it's relatively prime to S, so it must divide y0 minus y1. Okay, so once we have that piece, what does that imply? Let's see what that implies. Well, it implies that y0 minus y1 is some multiple of r, right? So let's call that multiple rt, where t is an element of the integers. And if we solve that guy for y1, what do we get? Let's see. So we would get y1 is equal to y0 minus rt, but we already know what r is. If I come back here and think about what r is that's the a is equal to a is equal to dr, so that means r is equal to a divided by d. And there's our first solution, for sure enough. y1 has to be the original solution, or the arbitrary solution, y0 minus an a over d, quantity a over d times t. Okay, if we substitute I don't know, let's see, what I would substitute in is probably this result, the y0 minus y1 into 2. So I'll just say this result into equation 2 back here. So equation 2, just to remind you, is this one. So if I substitute y0 minus y1, probably up here, then that means that I can put RT in for y0 minus y1. And what we'll find, well, let's just go ahead and do it. It would be R times x1 minus x0 is equal to S times what y0 minus y1, which in this case is RT. So I can see that that the r's will cancel left and right, and if I solve for x1, I'll get x1 equals x0 plus, let's see, dividing through by r, it'll be st, and solving for s in our previous result, writing it in terms of d's, a's, and b's, it'll be x0 plus b over dt. Okay. So what that means is that these are the general results, I guess, if you're given a specific result. And one way to show they satisfy ax plus by equals c is to plug them in. So we could say that these satisfy ax plus by equals c, no matter what t, because, well, let's just plug them in. So a times x1 plus b times y1 would be the same thing as a times x0 plus b over dt plus b times y0 minus a over dt. Putting ax0 plus by0 together, we get that, and then let's see, we would have an ab over d over over dt, and then here I'd have an ab over dt but negative, And so you can see here that this is equal to C, and you can see here this is equal to 0. So A times y1 plus B times y1 is always going to be equal to C no matter what the t, because we can see that the t's go away right here. So what does that really mean? I guess it means that we've created an infinite number of solutions because we can choose t however we'd like it to be, any integer. So we can conclude that there are an infinite number of solutions, one for every t in the integers of form x equals x naught plus b over dt, and y equals y naught minus a over dt. And that's what we wanted to show, right? Which is what we set out to prove. And we can end it right there. All right, so I hope that makes sense. Let's go ahead and go back to the slides and talk a little bit about how we can use this. So let's go ahead and pick a little bit harder of a Diophantine equation. Let's do 15x plus 21y equals 261. And we'll go ahead and solve this and use our newfound tool to do so. All right, well, I better make that bigger. Okay. All right, so let me get some new space out here. All right. So 15x plus 21y equals 261. Let's try it. So 15x plus 21y is equal to 261. Well, probably the first thing we should notice is that the to check to see if the GCD allows a solution. So let's go ahead and use the Euclidean algorithm to find the GCD. So we'll write 21 as 15 times 1 plus 6. Okay, so that would mean then 15 would be 2 times 6 plus 3. And then I would just write 6 as a multiple of 3. It's 2 times 3 plus 0. So I guess what have I found? I found that the GCD is 3. Okay. And so does 3 divide 261? So let's try it. 261 divided by 3. Let's see, 3 times 7, 3 times 8. 3 times 9, no, 3 times 8, so 8 would be 24, at least 21, that's 7. So that means indeed a solution exists, because indeed 3 divides 261. So how would I say that? I would say since the GCD of 15 and 21 equals 3, and 3 divides 261, solutions exist. Okay, so this is really simple now. All we need to find is a particular solution. So so we need to find an x naught, y naught, and once we have that, then we can simply pull off what we need. So right now we know that this guy up here, we would think of that as your A, this is your B, and this is your C. And well, we know A and B. We do know also that the GCD here 3, that's equal to our D in the solution setting for the general solution for Diophantine equations. So all we need really now is an x naught and a y naught. So how do we find that? We need x naught and a y naught So what is that? That's an initial solution. That's some x, some y that satisfies this equation, right? So how do we find that? One way we found to do that, to find a linear combination equal to this number, is to rewrite the GCD, right? So let's do it that way. So we know we can always find a linear combination of 15 and 21 equal to the GCD, and then since 261 is a multiple of the GCD, we can just scale it up to find the particular x naught, y naught we need. So I'm going to come over here and see if I can do this. If we know what we want to write it as is as a linear combination of 15 and 21 equal to 3, we'll start with 3 and say that 3 is equal to 15 minus 2 times 6. And then I'd replace 6 with what I can from the first line. So 3 would be equal to 15 minus 2 times, let's see, 6 can be written as 21 minus 15. And so what do we get? We get 3 is equal to 3 times, let's see, 15 times 3, and 21 times negative 2. And so I can see that here is an x naught, y naught that make it such that the linear combination equals the GCD, but the number we want it to equal is 261. We know that 3 times 87 is 261, so if I multiply by 87, I can get 261 here. And that means I have to multiply the right-hand side by 87. And so let's see, if I multiply 3 times 87, I get 261. So 15 times 261. And if I multiply negative 2 times 87, I get negative 174. And so there's a linear combination of 15 and 21, which are equal to 261. So what have we found? We've just found our x naught, y naught, right? So this is my x naught, and that's my y naught. And once I have that, I pretty much have the problem gutted, right? I mean, I know all the parts and pieces I need to just simply plug into the general form. And so let's do that next. So what do we know from the general form? So let's see. X naught, y naught are equal to, just to make sure this is clear to everyone, 261 and negative 174. So what do we have? X is equal to x naught plus a b over d times t, and y is equal to y naught minus an a over d t, correct? And let's see, so that means x is going to be equal to x naught 261 plus b over d. Let's see, so b is 21 and d is 3, so 21 over 3 t, which simplifies to 261 plus 7t, okay? And let's see, y is going to be y naught, x y naught, so it's negative 174 minus, let's see, a over dt, so let's see, a is 15, so 15 divided by the GCD 3 times t, so that means y is equal to negative 174 minus 5t, and those would be the two general solutions for this particular Diophantine equation. So in other words, when I'm given 15x plus 21y equals 261, then 261 comma negative 174 is one solution, and then for every t in the integers, there is another set of solutions, so an infinite number of solutions. Let's see if we can go to our example, or go to this same example using technology, just to give you a sense of you have the right answer here. So let's go here to, this is a sheet that I modified now to give you a sense of what's going on in Diophantine equations. So what do we have for A? We have 15. For B, we have 21. And for C, we have 261. Okay, so GCD is 3. That's what we discovered. And if I go here, then I have all the linear combinations of 15 and 21. And it's searching for 261 to be the total. So in other words, it'll highlight in red whenever it sees a 261. Now initially it appears that there are no solutions here, but we found that there indeed were, that if you start, let's see, we should have a solution, let's see, when 15, the initial solution was 261 and negative 174, so let's see, 261 and negative 174. We should get a solution, and indeed there it is. That's the first solution we got when I multiply x by 261 and y by, so in effect these are my x naught, y naught, and indeed when I plug them into ax and by and sum, I get 261, which is what I think I should get. But one of the things to keep in mind is that we should get a new value in the x sense. If I go back to this thing steps by 7 is what we're told, so 7t. Okay, so if I step that one by 7, and if I step this one by negative 5, okay, there they are. So in other words, if I take 7 more, than 261, so that's the 7t, right? That's the 7t in our solution. And if I take 5 less than the initial solution, I should get another. And certainly what happens is if you plug in the right coefficient for t for both your x and y here and here, then what you should see is a stair-stepping set of solutions, which are, of course, infinite in both directions because I've chosen the right slope in the matrix here, grid. So I hope that makes sense to you, a nice way to check your answer, although you kind of have to know the answer to go find it, but it is a nice way to check it. Okay. So let's see, one more question. Let's go ahead and solve this question from earlier on, right? We think that 100 bushels of grain distributed to 100 people, such a way that each man receives 3 bushels, woman receives 2, and child receives half. How many men, women, and children are there? Okay, so let's go ahead and switch over to our image, and we'll finish on this problem. So we left off with this problem with a Diophantine equation. You can go back in the video if you'd like to, but where we left off when we first looked at it as an example problem was here. We said it was 5m plus 3w equals 100, right? So again, I just want to make sure you notice here what I have is an A, a B, and a C, right? So let's see. Let's just play the game like we would normally. Let's try to write a linear combination of 5 and 3 as its GCD. So that means 5 should be equal to 3 times 1 plus 2, so division with remainder. 3 should be equal to 2 times 1 plus 1. And let's see, 2 is equal to 2 times 1 plus 0. So what does that mean? That means that the GCD of 5 and 3 must be equal to 1. That's the same thing as our D in this setting. So we should be able to write 5 and 3 as a linear combination equals 1 and then scale it up by 100 to get a particular solution. So let's go ahead and do that next. So shifting gears and sort of reversing the Euclidean algorithm, what we would write is 1 is equal to 3 minus 2. Now 2 can be written as 5s and 3s. So let's see, 1 is equal to 3 minus 5 minus 3. So that means 1 can be written as 3 minus a negative 3, negative 1 times 5. So it looks like it's 5 times negative 1 plus 3 times 2. So negative 1, 2 is an x naught, y naught. Oh, not yet. No, we've got to scale it up to be 100, right? So what would I do there? I would multiply this by 100. And if I do that, I want to keep the 5 and the 3 the same, but I would write it as 5 times negative 100 plus 3 times positive 200. So what does that mean? That means that in this particular solution setting, m naught is what, negative 100, and W naught is equal to 200. And of course, just check it. This is 600. This is minus 500. So 600 minus 500 is 100. Yeah, we're good. Okay, so we've got an M naught, Y naught, or W naught, so we can find solutions now quite easily. We can say that M, let's do the M one first. M is going to be equal to M naught plus the b over d times t. So I'm just switching out variables here. Of course, this was x and x naught in our original general solution, but we'll keep it contextualized with m. So what does m look like? M looks like this. It's m naught negative 100 plus b over d. So let's see, 3 over what we think d to be, which is just 1. So it'd just be 3 over 1 times t. So the number of men involved here is always negative 100 plus 3t. Okay, well, that's interesting. Let's go after the women now. So how would W equal? Well, it would take the initial solution and then we'd subtract to it, subtract from it, sorry, A over D. That's an A and that's supposed to be a D, T. So that would look like this. W naught we've said was 200 and we'd subtract A, which is 5, over D, which is 1, T. So the number of women involved has to always be 200 minus 5T. And it kind of appears that we've got a solution now, but you know, it'd be in this particular context, there's some more restrictions. I don't know if you noticed, but we've got these two solutions, right? We've got m is negative 100 plus 3t and y is 200 minus 3t, but we've got some constraints, right? I'll go over here. Well, no, I'll just keep on here. But we know that m has to be strictly greater than or equal to 0, and we know that w has to be strictly greater than or equal to 0. We could also say they have to be less than or equal to 100, but I think that'll come out in the wash here. Let's start with the first case. If m is greater than or equal to 0, then so let's start with case 1, m greater than or equal to 0. What does that mean? That means that what m is, which is negative 100 plus 3t, that's got to be greater than or equal to 0. So if I add 100 to both sides, I get 3t has to be greater than or equal to 100, and t has to be greater than or equal to 33 1/3. And well, you know, since t is an integer, we could say that t has to be greater than or equal to 34. Okay. So let's play this game again using the women. So if we say that the number of women has to be strictly greater than or equal to 0, what we're really stating is that 200 minus 5t has to be greater than or equal to 0. So negative 5t greater than or equal to negative 200. Dividing through by negative 5 and switching our sign, what we get is less than or equal to 40. And so that's kind of nice because what we know about t, in order for men and women to be non-negative, is that t has to be between 34 and 40. So what does that imply? I mean, what it implies, I guess, is that there's 7 solutions. Is that right? 6 or 7? 7 solutions, right? 1 for 34, 1 for 40, and 1 for every integer in between. So we could, if we had some time on our hands and were interested, we could find all the possible solutions here, right? So one way to think about this is just setting t equal to 34 and finding out how many men, women, and then children there are. So let's think about this. If t is 34, if you plug into our solution, what you'll find is that you'll get 2 men. If you put 34 in here, 3 times 34 will give you 102. 102 minus 100 will give you 2 men. If you plug 34 into the women's equation, what you'll find out is that's 30 women. And the number of children then, of course, remember this has to sum to 100. So once we've picked men and women, we know take it away from 100 and you have children. So 68, I believe, is correct there. So that's one set of solutions. Let's try the next one. If t is 35, then what happens here? We get 5, we get 25, and we get 70 kids. If t is 36, then here we get 8, and here we get 20, and here we get 72. So you can see some arithmetic sequences going on here. 37, 38, 39, 40. So let's think about this as going up by 3, up by 3. So my guess for 37 would be 11, and I am correct because I already did this. And indeed, this, I think this will proceed arithmetically, so I'll just fill it out. 14, 17, 20, let's see, 30, so 15, I'd go down by 5, 10, 5, and 0. And let's see, children are going to be 76, 78, and 80. I think it's kind of interesting to look at the table because it gives you a sense of why you get what you do. I mean, you can see that on the top, what we've done is sort of maximize the number of women. On the bottom, what we've done is maximize the number of men. And it appears that children, you know, are kind of strictly between 68 and 80. And I believe the reason that, you know, we never get close to 0 on children has to do with the limitation on the bushels. That we just simply, since we have a limited number of bushels, we have to give most of them to the children because the children require the least amount. Let's go to the technology just to confirm this. If I go back to my GCD calculator, I guess what we have here is a 3. Is that right? Let's see. It would be, is that what we put as our first one? No, 5. Let's call this 5 and this 3. And we want that equal to 100. If we go into our calculator, then we thought we got a first initial solution. Where was that initial solution? Negative 100 for the x, so negative 100 for the, oops. So let's just leave that as 5. This is negative 100 as our initial solution for x and our positive 200 for y. So sure enough, we can get solutions there. But do you notice everything here is negative, right? What we'd like, and everything here is over 100, right? So using what we know about the stepping of the function, when we solve for the general solution, we think that to get the x term, we're going to step by 3, and to get the y term, we're going to step by just 5, or negative 5, sorry. And here are the solutions, and I can see that all of these are valid Diophantine solutions, but in the context of our problem, they all contain at least one negative, right? So let's go ahead and bump this up to, I guess, 0 and see if we get any solutions. Well, we don't, right? Because x could never be 0, but we did find that x could be 2, didn't we? And then y, of course, one of the solutions we found was that y, which is women in this case, was 30. And so there they come up again. So if we start with 2 and we start with 30 and we step the 2's by 3, the initial solution by 3, and we step this other initial solution by 3, then I think what we're seeing here are all the possible solutions, and I think they're all, let's see if I can get it right here. I think that's them right there, right? Because beyond that, either x or y, which in this case are the number of men and women respectively, has to be less than 0, right? So I think those are the 7 solutions that we found. Another way to sort of check this would be to use Excel to create a table of solutions. So when t is equal to 30, here I've put the Diophantine general answer, I guess, for men and women. So this would be 100 plus 3t, and this would be, what is it, 100 minus, oh, that's actually wrong. So this should be equal to 100 minus 5t. Oops, sorry. That's equal to 100 minus 5 times t. Sorry. So t, there we go. Thought I had this correct. Okay. Oh, I did have it right to begin with. Sorry, it's 200. Yeah, we're okay. Sorry. It is 200 minus 5 times t. I did get that right, I think, on the explanation. So what we're looking for is the value of t where men and women are both positive, and I think you can see them in here. And what I did also was did a little bit of a check. Certainly these three are equal to sum to 100, but do the bushels really work out is the question. So what I did in this column is I went ahead and summed 3 times M, so 3 bushels per man, 2 times W, or 3 per woman, plus a half times C, and sure enough, they do all check out. So the solutions that, in this case, satisfy the question are 7, and those are all the possibilities that are out there. Okay, so hopefully this made some sense about what Diophantine equations are and the general solution method, and even a problem from history that can be solved to its 7 unique solutions. So I wish you luck on your homework, and I'll see you on Monday when I get back.